We're now going to cover permutations and combinations. Now, suppose we're given n different items, then a permutation of r of those items selected from the n without replacement is an arrangement where ordering does matter. So that's what a permutation is. For example, if you're given the numbers 1, 2, 3, 4, 5, so these would be the n items that you're given that are being referred to up here. So these are your n items. And you select 3 from those n items, let's say. So the r would be 3. And you create the number 354. This is what we call a permutation. So you selected 3 items from the numbers 1, 2, 3, 4, 5, and here's your permutation, 354. Now we would consider 453 to be another and distinct permutation. So this is a different permutation from this one, you see, because we said ordering does matter. So we consider these two permutations to be different. So both of them are then counted in the total number of permutations that are available to us. Now it's a fact that if you have n items and you select r items from those n without replacement, here's the formula for how many permutations you have. You will have n factorial divided by n minus r factorial possible permutations. Now most calculators and computers like Excel have the permutation function built into them, so you don't have to normally evaluate this, although it's not really that hard. We can check it out. So let's look at this example. If you're given the numbers 1 through 9, so you have 10 items here. So here the n is equal to 10. Find the number of permutations of 4 items selected from these 10. So this is our r right here. The r is 4. So our answer is simply going to be 10p4, where the n is 10 and the r is 4. Let's write that down here. N is 10 and the r is 4. And so this is simply going to be, using this formula up here, 10 factorial divided by 10 minus 4 factorial. And so 10 minus 4 is 6, so this is 10 factorial divided by 6 factorial. Now we need to calculate that out. Now like I said, calculators and Excel have this built into, have the permutation formula built into them, so we don't really have to even calculate that out. Let's just use the permutation function on the calculator. So the permutation function is here on your calculator. Now we want to evaluate 10p4. So first of all, type in 10. Now this is on the TI-83. I'll show you how to do it in Excel as well. Then go into Math, press the Math button, go over to Probability, and you see the NPR there. That's the number 2, so click on number 2, and then type in the number 4. So we're doing 10p4. And now hit Enter, and there's our answer, 5,040. So this number down here would be 5,040. If we evaluated 10 factorial divided by 6 factorial, that's exactly what we would get. We can check it out here. 10 factorial divided by 6 factorial. Oops, that's not what I want. Let me start that over again. 10 factorial divided by 6 factorial, and we get, same thing, 5,040. So we can just use the built-in NPR function on the calculator. Excel also has that. I'll show you that. So in Excel, you can just type it in like this. Equals. Excel has a function called permute. P-E-R-M right there. Permute. U-T. Permute. And we have 10 items, and we want to select 4 items from those 10. And there you go, 5040. So once again, that's what you would type in. Equals P-E-R-M-U-T, parenthesis 10, 40. So, and once again, just make sure you understand that when we select 4 items from these 10, we're selecting things like 1, 4, 0, 8. That's one possible permutation of selecting 4 from these 10. And then 4, 1, 8, 0 would be a different one, and so on. So there are 5040 possible permutations of 4 items selected from these 10. Let's take a look at this problem. So we have a committee of 12 people, and we want to find the number of ways of selecting a president, vice president, treasurer, and secretary. Now, note here that ordering does matter, so this is going to be a permutation problem. So why does ordering matter when we select these 4 people? Well, if we select Joe, Sue, David, and Lisa, let's say, so Joe would be president, Sue would be vice president, David would be treasurer, and Lisa would be secretary. You see, ordering matters because this would be different than if we selected Lisa, David, Sue, and Joe like this. Now Lisa's the president, David would be the vice president, Sue would be the treasurer, and Joe would be the secretary. So you see, this is a different slate of candidates. So ordering does matter. So the number of possible slates of candidates that we would have here would be 12P4. We want to select 4 people from 12, and ordering does matter. And now here I've opened up Excel, so let's evaluate 12P4 using Excel. So if we just type into any cell in the spreadsheet, equals P-E-R-M-U-T, parenthesis 12, 4, close parenthesis, hit enter, and there you have it. So 12P4, or 12 permute 4, is 11,880. So there are 11,880 possible slates of 4 candidates selected from that group of 12. And now let me show you how to also evaluate that using a typical calculator like the TI-83. Let's just evaluate 12P4, 12, math, we go over to probability, NPR is number 2, and 4. And there we go, 11,880. So that's our answer. So 12P4 is 11,880, and that's how many possible ways we would have of selecting a president, vice president, treasurer, and secretary from these 12 people. Once again, keep in mind for permutations, ordering does matter. Now let's take a look at combinations where ordering does not matter. So now we're going to look at combinations. So suppose we're given n different items, then a combination of R of the items selected from n, from the n items without replacement, is an arrangement where ordering does not matter now. So for example, if you're given the numbers 1, 2, 3, 4, 5, and you select the numbers 3, 5, 4 from those, then we consider 3, 5, 4 to be the same as 4, 5, 3, and that's the same as 3, 4, 5, and that's the same as, 5, 3, 4, and so on. So all of these are the same. We don't consider them to be different in any way. It's sort of like if you play the lottery, many lotteries, it doesn't matter the ordering that the numbers come up in, right? For example, if you have a bin containing 49 balls and you select whatever 6 numbers on your ticket, it doesn't matter what the ordering is that those numbers come up in. You don't have to match the ordering. You just have to match what numbers come up. That's a combination problem then. So the number of combinations that are available given n items is given by this formula. NCR equals n factorial divided by r factorial times n minus r factorial. It looks a lot like the permutation formula, except you have this r factorial right here in the denominator that's included in the denominator. Otherwise, this is the permutation formula right here. Now, once again, most calculators and Excel has a combination formula built into them, so we don't normally have to type this in. We can just do like we did with permutations, just use the built-in function. So for example, suppose we're given the numbers 0 through 9 again. We want to find how many combinations of 4 numbers selected from these 10 that there are. So in this case now, as with the permutation problem, our n is 10, our r is 4 again, and so our answer is going to be 10C4. Now sometimes, just some notation here, sometimes you'll see this written as like this. So it sort of looks like a fraction, but you don't have the horizontal bar there and you put parentheses around it. Sometimes you see a combination written like that. Now let's use our calculator to evaluate this. And so we would enter that as 10, and then we have to find the combination button. So once again, you go into Math on a TI calculator, over to Probability, and then NCR is number 3. Oops. Go down, or hit the number 3. And then type in 4, and hit Enter, and there you go. So this is 210. If you remember back to the previous problem, we saw there were 5,040 permutations. So there are far fewer combinations than permutations, which makes sense because, if we think about this, for the permutation, for the combinations, we are lumping a lot of outcomes together as one. For example, up here, we're considering like 3, 4, 5, 3, 5, 4, 5, 3, 4. They're all the same. So when you're dealing with combinations, you're taking a lot of your permutations and lumping them into one result. So that's why you have far fewer combinations. And of course, you could evaluate this using the formula up here as 10 factorial divided by 4 factorial times 10 minus 4 factorial, which is 10 factorial over 4 factorial times 6 factorial. And if you evaluate this on the calculator, you will get 210. Let's just do that quickly. So if we evaluate 10 factorial divided by, and we have to put in parentheses 4 factorial times 6 factorial. So there's the actual permutation formula. There you go. It's the same thing, 210. Let's do this in Excel. I'll put in that cell right there. That was our permutation, 10P4 right there. So here we're going to do 10C4, so equals. Now, Excel has a combo function built in, COMBIN, parenthesis 10, 4. That's how you would enter it. hit enter, and there you go, 210. Let's take a look at this problem. So now we have a committee of 12 people again, and now we want to find the number of ways of selecting a subcommittee of 4 people. Now when we select the subcommittee, note that ordering does not matter in this case, right? Before it mattered because we were selecting a president, vice president, treasurer, and secretary. But now when we select a subcommittee, there's nothing special about the ordering anymore. So since there's nothing special about the ordering, if we were to select Joe, Sue, Lisa, and Dave, that's the same as if we selected Lisa, Sue, Dave, and Joe. These are the same. They're just 4 people on a subcommittee. There's nothing special about the ordering. So this is a combination problem now, and our answer is going to be 12C4. And let's use the calculator or Excel to evaluate that. On the calculator, that would be 12 NCR4. And we see there are 495 possible subcommittees that we could create. Notice that this is much smaller than 12P4, which was 11,880, because we're taking a lot of these results down, a lot of these permutations down here, and lumping them together into one, because we don't care about ordering with combinations. So we take a lot of these and just lump them together into one possible outcome. And there you go. Alright, so that concludes this brief discussion about permutations and combinations.